So good morning, everyone. Uh, Good morning, everyone, and welcome to the 12th week of problem-solving session in basic electrical engineering. And today we will be doing practice problems for the 12th week content, that is calculation of steady-state responses in circuits with inductors and capacitors. So let's start with it. Now, so let's start with the first question. So it's a low pass RC filter, and in this you have been given that voltage source, a sinusoidal voltage source with frequency with an amplitude of 6 and frequency of 2 root 2 into 10 to the power 6 radian per second is applied to this low pass filter with 1 kilo ohm of capacitor, 1 kilo ohm of resistor, and 1 nanofarad of capacitor. And in the steady state, we need to find out what is the output, and what terms we need to find out in the output are in the omega, the amplitude, the frequency. Frequency, of course, will be same because in all the LTI systems, the frequencies don't change. So frequency over here will be 2 root 2 only. So omega is 2 root 2 into 10 to the power 6 radian per second. And we need to find out the amplitude and the phase shift created. So let's try to solve this. Now we know that in steady state, when the circuit has reached steady state, the Laplace domain can be replaced by the frequency domain, that is S can be replaced by j omega. And due to that, what we have over here is, this is a 1 kilo ohm of this is resistance R, and we have capacitance as 1 upon j omega c, and we have Vs. So V out in terms of Vs, we can write it as V out is equal to, now there will be resistor divider, sorry, impedance divider. It's because these are not resistors, these are impedances. And impedance divider will be the impedance of the capacitor, that is 1 upon j omega c divided by R plus 1 upon j omega c, and this gets multiplied by Vs. So the transfer function is 1 upon 1 plus j omega rc. Okay. Now we plug in the values also. The magnitude will be, and so this is h of j omega, and the magnitude response will be the magnitude of this, that is 1 upon square root of the real part square plus imaginary part square. The real part is 1 squared and imaginary part squared is omega square r square c square. And the phase of this will be at h of j omega will be, since this is in the complex number is in denominator, so you will have negative sign of tan inverse real part by imaginary part, and real part is 1. So you will have tan inverse omega rc. Now let's put in the values of rc and omega. We know that omega is equal to 2 root 2 into 10 to the power 6. R is 1 kilo ohms, and C is 1 nanofarad. So what we have over here is, the magnitude. We already, the magnitude is given of input as 6, So the final VP will be 6 into 1 upon square root of 1 plus omega square. Omega square is 4 into 2 into 10 to the power 12 into r square. R square, that is 10 to the power 6, into c square, that is 10 to the power minus 18. And what this comes out to be, 6 into 1 by 1 plus 8, and so the 10th power will all be cancelled, and this is 6 by square root 9, this is 2. So 6 by 3, this is 2. So this is our VP, and as far as phase is concerned, phase will be the phi part will be minus of tan inverse 2 root 2 into 10 to the power 6 into RC. R is 10 to the power 3 and C is 10 to the power minus 9. So again, 10 to the power 6, 10 to the power minus 9. Yeah, correct. So again, the exponentials are cancelled, and what we have at the end is minus of tan inverse 2 root 2. So this can be computed in either degrees or radians. Yeah, we will leave it to that form. So yeah, this is how you need to solve this question. Now let's move on to the next question. So in this question, you have to again, you have been given a sinusoidal voltage source to a RLC network, but the output voltage you don't need to find at the output of the capacitor, but you need to find the output voltage across this series combination of inductor and capacitor. So again, you need to find the amplitude and phase. So how you will go about it? Again, for inductance, the impedance ZL is equal to J omega L, and for capacitance, the impedance ZC is equal to 1 upon J omega C. So what we have over here is the circuit looks as follows. So this is ZR, and this is overall ZL plus ZC, and here you need to find out the output, that is V1, from Vs to V1. So now in this question, again, it will be the transfer function will be found out by uh, impedance divider, and h of j omega will be equal to ZL plus ZC divided by ZR plus ZL plus ZC, and now the value of ZL will be, so from the given values it will be uh, okay. So let's first find it out in terms of variables, and then we will plug in the numbers that are given in the question. So j omega L plus 1 upon j omega C divided by R plus 1 upon j omega C plus j omega L. And this comes out to be 1 minus j omega squared LC divided by j omega squared LC plus j omega RC plus 1. So now j square, as you all know, is equal to minus 1. Sorry, this will be plus over here. And j square will be equal to minus 1. So Let's take this to the fresh page. So what we have over here is 1 minus omega square LC divided by minus omega squared LC plus j omega RC plus 1. Now, this is a complicated expression, and to do the sanity check, you can look whether this expression makes sense or not. So, uh, let's try to find out what will happen at omega equal to 0. So at omega equal to 0, your inductance will be short circuited and your the capacitance impedance will be infinite. So the voltage from Vs to V1 will the transfer function will be equal to 1 because this resistor won't have any voltage drop across it if it has any capacitor in series in case of DC. That is omega equal to 0. And do we have it over here? If we put the value of omega equal to 0 in our derived expression, the term of omega square goes to 0, and in denominator also the term with omega square and omega goes to 0, and we get h of j 0 as equal to 1. So uh, this matches the uh, expression. And let's see what happens at omega equal to infinite. At omega equal to infinite, your the impedance of capacitance will go to 0, and impedance of inductance, since it's j omega L, and if omega tends to infinity, the impedance of inductance will go to infinity. So again, the voltage from input to output will be equal to the transfer function from input to output will be equal to 1, and no voltage drop will be there across this resistor. So in this case, again, the h of j infinity should be equal to 1. And does this comply with our derived expression? So in this case, about putting limit omega tending to infinity. In this case, only the terms with the highest power, that is omega square in the numerator and omega square in the denominator, are dominating in that. And in this case, since the coefficient of omega square in numerator and denominator are same, so from this expression also we get h of j infinity as equal to 1. So this expression that we derived makes sense. Now let's plug in the values, and now next thing, we need to find the magnitude and phase responses separately. So the magnitude response in this case will be the numerator is completely a real value because 1 minus omega square LC, this is a complete real value. So the magnitude is 1 minus omega square LC divided by, now in denominator we will have the squared, the magnitude will be computed as square root of real part square plus imaginary part square. Now the real part is 1 minus omega square LC, it's squared, plus the imaginary part is omega square r square c square. Okay. So in this case now, and the numerator won't have any phase shift as numerator is completely real, and in this case only the denominator will contribute to phase shift. So the phase can be written as, now since again the complex number is in denominator, so while computing the phase we will have a negative sign minus tan inverse imaginary part divided by real part. So the imaginary part is omega RC, that divided by 1 minus omega square LC. So these are the expressions for magnitude and phase responses. Now Let's see, the omega that is given in question is 10 to the power 6. Inductance is given as 1 microhenry, that is 10 to the power minus 6. The capacitance is given as 1 nanofarad, that is 10 to the power minus 9. And the resistance is given as 1 kilo ohms, that is 10 to the power 3. So the natural frequency of this thing is okay. So now the product LC will be 10 to the power minus 15. Uh, okay. So yeah, the product LC will be 10 to the power minus 15, and the omega that is given is 10 to the power 6. So if we plug in the values, what we get as the magnitude response is 1 minus 10 to the power 12 into 10 to the power minus 15 divided by 1 minus 10 to the power 12 into 10 to the power minus 15 whole squared plus 10 to the power 12 into r square. That r square is 10 to the power 6 into c squared, that is 10 to the power minus 18. So this complete thing can be cancelled. So this all goes to 1. And here, if we see, then the the expression that we come, the final power of 10 that we get from here is 10 to the power minus 3. Now 10 to the power minus 3 is much smaller than 1, so this value can be approximate. So this value over here and over here can be ignored, and this the magnitude response will be almost equal to 1. Now the phase response. So let's copy the phase response from here. The phase response will be minus of tan inverse 10 to the power 6 into 10 to the power 3. Oh, wait for a minute. Yeah, into 10 to the power minus 9 divided by 1 minus 10 to the power 12 into 10 to the power minus of 15. So this can be written as, now the numerator goes to 1, and again in denominator, and the it's 1 minus 10 to the power minus 3. So this thing is approximately equal to 1 again. And if it is equal to 1, so it's tan inverse 1. And tan inverse 1, we know that it's minus 45 degrees. Just a minute. Mm, okay, yeah. So the magnitude will hardly be affected. The magnitude, whatever came in as a 5, that will, the magnitude Vp will be approximately equal to 5, and we will see a phase shift of minus 45 degrees in the final output. So this is how you needed to solve it. So the point is that you can apply approximations. You don't need to be precise till last decimal point. You can use your approximations and get to the answers. So let's see the next question. Now, in this question, there are two independent sources. One is and this is being applied to an RLC network. One is over here is a voltage source, and other is a current source. And the important thing to note is they have the same frequencies, but they have different phases. Now, like had there been same frequency and same phases, okay. So in this case, we can either use phasors. So we can denote the we can denote both voltage and current uh, values as phasors. So how we'll do that? So we'll write the we'll basically write the magnitude, and then in phase its phase. Now we will consider cos as 0 degree phase, and we know that the sine is basically, so we have sine is basically pi by 2 phase shifted cos. So uh, the sine can be written as, so we have uh, 3 0 degrees as Vs, and Is over here is, so we can either write it as 4 with a phase shift of minus pi by 2, and or we can write it with the iota form, that is 4 and j minus j. So we have these two things. So now we can solve the question. So first of all, let's check what is the natural frequency of this. Now, natural frequency, again, it's same as the previous one, is 10 to the power minus root of 10 to the power minus 15. So yeah, we need to solve this again. So now V naught over here. So we will apply the superposition to solve this question. So first of all, only due to the Vs, we will try to find out the transfer function. Only due to the Vs, we have j omega L, the resistance, and the capacitance impedance, that is 1 upon j omega c. So this is a low pass second order filter. So the standard value of its transfer function is 1 upon minus omega square LC plus j omega RC plus 1. Yeah. So this is due to the Vs, and due to the current. So in case of current, we will short circuit the Vs. What we get then is, we get this kind of circuit. So now we do the calculation. So now again, this circuit can be written as follows. So with the impedance transformation, we can apply impedance transformation on this part of the circuit, and this will yield a series resistance of R and a voltage source of Is times R, an inductor, and a capacitor. So again, if we consider this source transformation, so for Is times R, so the value of output V out at capacitance will be R times Is times R. So again, this is a, second order low pass filter. So the expression will be same as that we got for simple voltage source. So this will be R times Is. So this is over here is Vs divided by minus omega square Lc plus j omega Rc plus 1. So we have these two things. Now we plug in the values of these and get the final answers. The magnitude response for so the magnitude and phase responses for both of them will be same because uh, the transfer functions are same. Only in case of Is, there will be a slight change, and that is due to this resistance getting added. So the magnitude, only due to Vs, what we have at the output is, so let's call it Vp1 cos omega t plus phi 1. So this is due to Vs, and due to Is where we have Vp2 cos omega t plus phi 2. So we have these two uh, expressions, and now we individually find out Vp1 phi 1 and Vp2 phi 2, and uh, so again the magnitude response j omega is 1 upon root under 1 minus omega square Lc whole square plus omega square R squared C squared, and the phase responses minus of tan inverse omega Rc divided by 1 minus omega squared Lc. So the value of omega that has been given is 10 to the power 6. The value of inductance is 10 to the power minus 6, and value of capacitance is 10 to the power minus 9, and value of resistance given is 10 to the power 3. So if we plug in the values, so what we get over here is, now omega p1 will be equal to the initial voltage, the voltage of input is 3. So omega p1 will be 3 into this expression. Now, if you plug in the values in this expression, again, as we saw in the previous problem, what we get over here is 1 minus 10 to the power 12 into 10 to the power minus 12 into 10 to the power minus, sorry, 10 to the power minus 6 into 10 to the power minus 9. power minus 9. So again, over here, this term will be much smaller than 1. So this term can be ignored. So this will be approximately equal to 3. Now, phase, phase due to this will be minus tan inverse 10 to the power 6 into 10 to the power 3 into 10 to the power minus 9 divided by 1 minus omega square LC. Now again, this is equal to 10 to the power minus 3, so this can be ignored. And the term in the numerator goes to 1, so this is minus 45 degrees. And the phase due to the phase shift for both the current input and the voltage input will be same. However, the final phase will be different in both the cases. So the final expression that you get for the output is, now again we shall calculate VP2 also. So VP2 is 10 to the power 3, that is the value of R times the current is given in milliamps, that is 4 into 10 to the power minus 3. And the magnitude response, as we saw over here, is approximately equal to 1, so that can be neglected. So we have over here is the magnitude due to the current comes out to be 4. So the final uh, V out can be written as 3 cos omega t minus 45 degrees plus 4 sin omega t minus 45 degrees. Okay, so now since the this term and this term are perpendicular, so in case if you write it as if you view it as phasor, so cos omega t and sin omega t are perpendicular to each other, and the overall magnitude that you will get from these two will be the sum squared of the two. So the cos is considered as 0 degrees. So this will be 3, this value will be 4, and what you will get over here is the value will be the square sum squared of 2, that is 3 square plus 4 square, that is equal to 5. And the phase that you will be getting is the additional phase from cos will be just the tan inverse of 3 by 4. So let's work it out. So the final magnitude is 5, and the phase will be cos of omega t. Now, initial minus 45 degrees is there anyways, and additional phase that will be added to this will be minus of tan inverse. So this is the phase of it, and this is so this over here is 4. So minus of tan inverse 4 by 3. So this is the phase, and 5 is the magnitude. So so with two voltage or with two sources, you should do the superposition thing, and from there you can get the values. Now this could also have been done as phasors. So in that case, what you would have done is you would have not went into the sine and cosine details. You would have just written as 3 and 0 degrees. Then this is j omega L, and over resistor, since it's a negative phase shift of pi by 2, so minus 4j. This is R, and here it is the capacitance. So you could have this is 1 upon j omega c. So you could have worked out the expression through this as well. And whatever you have got at the output, final output, will be some V naught with some phase of phi naught. So that you could this phase would have been so you would have got V naught as a complex equation, a complex expression, that is A plus J beta, and the magnitude would have been root under A square plus B square, and the phase would have been tan inverse B by A. Okay, so let's move to the next question. Now, in this question, again, you need to find out for sinusoidal input. You need to find out the output uh, voltage. So, in this case, first of all, you should see what is the natural frequency. The natural frequency in this case is 1 upon root under LC. So this is a second order low pass filter. So the natural frequency for this will be 1 upon root under LC. And let's see if the input is at the resonant or natural frequency. So let's plug in the values. There is 10 into 10 to the power minus 3 into 2.5 into 10 to the power minus 3. Now this comes out to be 1 upon 5 into 10 to the power 3. So, so this comes out to be 200, and this makes our job a little easier over here. So in this case, what would happen? The transfer function from input to output will be the standard second order low pass transfer function, that is 1 upon minus omega square LC plus j omega RC plus 1, that is equal to BO by B in. And since the omega input is equal to 1 upon root LC, so this term would have gone to 1. So sorry, minus 1. So this minus 1 and 1 will be cancelled. So at the end, what you have only over here is 1 upon j omega RC. So if you plug in the values, j into omega is 200 into the resistance given is 4, and the capacitance value is 2.5 into 10 to the power minus 3. So this comes out to be minus j into 1000 by 800 into 2.5. Let's calculate this. 7.5. This comes out to be 0.5. Yeah, this is 0 times j. Now the input is 5 sine 200t. So now minus j basically means that there is a phase shift of minus of 90 degrees in so minus j corresponds to phase shift of minus 90 degrees from the input. So what you have finally is 5 into 0.5 sine 200. So this is the value of output, 5 into 0.5, 0.5 due to the magnitude response, sine 200t minus 90 degrees. So this is 2.5 sine 200t minus 90. Now this is equal to, so cos, so sine 90 minus theta is equal to cos theta. So this can be applied over here. So what you have over here is minus 2.5 cos 200t. So this is the value that you get. Now you need to find the output in terms of cos itself. So what is the value of b? The value of b is minus 2.5 and value of theta is equal to 0. So this is how you need to solve this question. So let's move on to the next question. Now, so earlier we saw an example of series RLC circuit. So now this one is a parallel RLC circuit, and the input is given as 2 cos t, and the final output. So this input is a current source of 2 cos t, and the final output we need to find the output voltage of this parallel RLC in terms of b sine omega t plus theta. So let's solve it. So the overall impedance that this current source will be seeing will be 1 ohm. This is j omega, as value of L is 1, and the capacitance as 1 upon j omega into value of capacitance, that is 2. So 2 cos t goes into this. So the equivalent impedance of these will be 1 by r plus, sorry, the equivalent reciprocal of equivalent impedance or admittance in this case will be 1 by r plus 1 by j omega plus j 2 omega. R is equal to 1, so it's 1, so it's j omega plus 1 plus j squared 2 omega squared, and now divided by j omega. So the equivalent impedance is j omega divided by minus 2 omega squared plus j omega plus 1. So again, the magnitude response. So this is going to, so this j omega, this z of j omega is basically the transfer function from the input current source to the output voltage, and the magnitude response we have is again the for the numerator it's omega, the magnitude is omega, and for denominator the square root of sum of real part and imaginary part, so that is 1 minus 2 omega squared whole squared plus omega squared. Now value of omega from the and the phase from here is, so the phase of the numerator is 90 degrees and phase for contribution of denominator is minus of tan inverse omega divided by 1 minus 2 omega square. So the imaginary part is j omega, so its coefficient comes as omega, and 1 minus 2 omega squared is the real part. So phase is as follows. Now From here, the magnitude, now we plug in the value of omega, that is equal to 1. So we have 1 divided by 1 minus 2 whole squared plus 1, that is equal to 1 by square root of 2, and the phase 90 minus tan inverse 1 by minus 1. So 90 minus tan of minus 1. So tan of minus 1 is minus 45 degrees. So it's 90 plus 45 degrees, that is equal to 135 degrees. So now the expression that we get finally is 2 by root 2 cos of omega t plus 90 plus 45 degrees. The omega is basically 1. Cos of t plus 90 plus 45 degrees. Now, again, so this can be written in form of sine as, so cos 90 plus theta is equal to minus sine theta. So what we have over here, 2 by root 2 comes out as root 2. So minus root 2 sine t plus 45 degrees. So the asked expression here is b sine omega t plus theta. So we have minus square root 2 as value of b, and theta is 45 degrees. So this is how you need to solve this question. Now let's move on to this question. So in this question again, so here you see that the so here you cannot directly apply the phasors. Now the problem is that the two input sources that are given have two different frequencies, so you cannot directly apply the phasor in this. So in this case you will have to resort to superposition. So now it's asked that what you will need to do in this case is de-energize one of the sources and find the impedance corresponding to the particular the frequency that is mentioned in the question, and solve this accordingly. So let's solve it for one of the input sources. So let's choose I1. So what we, and inductance in series to any current source is doesn't has any impact on the circuit. So I1 goes to this network. Now, since this is open circuit, so again, this 2 Henry inductance is of no impact. So we have 10 ohms. Then we have J omega zero point 0.4, and we have 1 upon J omega C. So let's call this L for technique. So we need to find V1 and V2. Now V1 basically will be, so for finding V1, the overall looking in impedance Z equivalent is 10 ohms into the impedance of this, that is j omega L plus 1 upon j omega C divided by 10 ohms plus j omega L plus 1 upon j omega C. So this comes out to be minus omega squared LC plus 1 into 10 divided by minus omega squared LC plus j omega 10 into C plus 1. So again, the sanity check. So for omega equal to 0, uh, all the current, so this will be an open circuit and all the current will flow inside the resistor. So the equivalent impedance you should have seen as 10 ohm resistor, and in the expression also that you have derived, if you put omega as all zeros, so you the numerator and denominator only will contain 1. So this is correct. And at infinite frequency, the capacitor will become open circuit. So in this case, again, the final impedance will be only due to the resistor. And that's what you are seeing in this, because minus omega square LC and minus omega square LC will be the term dominating at very high frequencies, and they will cancel each other, and you will end up with an impedance of 10. So this is what will be V1. So V1 basically will be I1 times this equivalent impedance, and V2 will be whatever you get as V1 into the resistor divider. Sorry, the impedance divider between the inductor and the capacitor. So this is Z equivalent 1, and the transfer function for V2 will be Z equivalent 2, and that will be equal to the same transfer function. First of all, 10 minus omega square LC plus 1 divided by minus omega squared LC plus j omega 10 into C plus 1 into the impedance divider, and impedance divider comes out to be 1 upon minus, so it's 1 by j omega C divided by 1 by j omega C plus j omega L. So this is equal to 10 into minus omega squared LC plus 1 divided by minus omega square LC plus j omega 10 C plus 1 to 1 upon 1 minus omega square LC. Now the second order pole and second order zero will cancel each other. So ultimately you have a low pass transfer function for node V2 due to current source I1, and that comes out to be 10 upon minus omega square LC plus j omega 10 into C plus 1. So again, the sanity check you can do. So for omega equal to 0, that is very low frequencies, the now this senses the impedance over looking in impedance from here is 10 ohms, so voltage developed will be 10 into I1, and all this voltage, since at omega equal to 0 your inductance is a short circuit, so all the voltage will come at V2 also. So the voltage at V2 will also be 10 into I1, and what you get over here from the derived expression, the omega square LC and this first order term containing omega will go to 0, and the impedance will be 10. So this is correct for low frequencies, and for higher, very high frequencies, again the impedance due to the inductance will be infinity, and impedance due to the capacitance will be 0. So the voltage developed at V2 will go to 0, and that is what we see from the expression also. Omega square LC term will become infinite, and 1 upon infinity will become 0. So this is how you now what you have to do to find the V1 values is plug in the value of omega L, C and R, and calculate the magnitude as well as phase. So this was about it from today's class. Thank you for attending.